Fugate at Naval Information Warfare Center in San Diego, and this is collaborative research between us and NSA Research. My co-author is Kimberly Ferguson-Walter in the back, and she'll be presenting some stuff on one of our human subject research studies later today, so stick around for that. So I'll go through what we mean by defender disadvantage, talk about cyber deception and the models that we're using for cyber deception, shortly discuss a 2015 pilot study that was run by NSA Research, and talk about game theory and how we are modeling cyber deception. And then talk about an example game and a formal definition, some new nomenclature that we think will be useful for others in modeling, explicitly modeling the deception and not just uncertainty in the adversary, but modeling of false information and false knowledge about the game structure. So we all know that the defender's horribly disadvantaged. We're truthful, the attackers are deceitful. We deal with this on a day-to-day basis, and this is a big problem. So we also have control asymmetries. Adversaries don't care about admin rights. They will just take them if they need them, if that's possible for them. We have ethical and legal asymmetries. There's all of these things that we have to deal with, and we constrain ourselves, in many cases rightly so. We also have bureaucratic asymmetries, sort of constraining our users to not be able to do the things, or even detect threats in some cases. We also have to deal with falsifiability of security claims. And so someone says, you must do something to make yourself more secure. It's very hard for us to think differently about that, and how do we change these sort of claims and make them a little stronger. And we all know these problems. So how can we decrease, or change or reverse these asymmetric disadvantages? So it should be obvious that we control our own cyber domains. The example I like to use is that we always have at our disposal sort of the nuclear option for disabling or destroying our own system, unplugging it right in order to make it confidential or secure in that method. But that kind of security is not usable. So can we use more fine-grained control? Can we use deception to give ourselves operational security in cyberspace? So can we mask or hide the properties of our systems, as Kevin was talking about earlier? Can we use mimicry or camouflage in order to cause our adversaries to think our systems are not what they really are? Can we inject false observables? So cyber deception, in my mind, is a calculated sort of exertion of control over our own systems. We want to present observation, prevent manipulation, interfere with attacker actions, misdirect their resources, cause them to do compute on our behalf if possible, and sort of try to dramatically increase their cost, dissuade them from even attempting to attack our networks because they're too annoying, too frustrating. So there's lots of things we can do. We think that these are all sort of things that are feasible. We can waste time, we can waste labor, we can create a sense of false knowledge or false success. We may even be able to create lasting cognitive bias effects, sort of affecting the psychology of the attacker. So getting them to believe something over a long period of time that causes them to have a long-term disadvantage. So these are all the potential benefits. But really, in order to get here, we have to be able to build environments that incorporate deception at every level. So I adamantly agree, with the sentiments by our keynote speaker that we need to put deception everywhere that we can think of putting it. And it can't just be static deception. It can't just be, it's really good to pre-stage deception in networks, but we have to go farther than that. We have to make our deception adaptive in the face of a changing adversary. So in 2015, having already started down this road of building a decoy platform, my colleagues at NSA Research ran a small pilot study. This is 3 professional red teamers over a period of 6 months with, or 6 months between each phase. And they're just basically doing recon on a network. So asked to sort of do recon if you can, give us information about like what the topology is and try to exfil, content. And this was interesting in that there's a lot of control over the study itself or what the red teamers would do, but we have a lot of really interesting information that we were able to sort of learn about what their thought process was. What kinds of things did they get tripped up on? What kinds of false features did they think were actually deception when they weren't? Oh, that shouldn't be blank. Okay, it's building out, so I'll just click through this. Let's go back. So this was really promising because they spent a lot of their time on the decoys when only a very few of the actual systems were decoys. And there was a lot of indications of cognitive bias effects. So things where they would fixate on a particular feature and then use that in hindsight to say, this new system I'm looking at looks just like the old one because it's got a different font, or something that's completely irrelevant to the use of or the properties of the decoys. So it turned out that these decoys are also effective even if the attackers know that they're there, and even if you take them away at the end. So this led to what Kimberly will talk about later today, which is this larger scale study with 139 red teamers looking at a similar environment, but a much more tightly controlled study with lots of great data. So if we're going to build a deception engine, our model is not that it can be static, it's got to be observing the environment. It has to be analyzing, sort of, and reorienting itself based upon those observations, making new decisions based upon what we have learned about an adversary, and then changing its behavior, performing manipulations of the network, of the state of the decoys, of the state of even real hosts, and maintaining that knowledge over a long period of time. So this kind of adaptive deception engine has to be both observing of the environment and observing of its own internal state and decisions being made. So we're using the MAPE-K model, and we're actually using Carnegie Mellon's framework called Rainbow to do experimentations, right, in an adaptive cyber deception. So trying to build a system that adapts its strategies, adapts the models that we're providing it over time. So we're using game theory as a means of framing a lot of the implementation that we're doing. So I'm not going to go through this, but basically we have players that have conflicting goals. They may be unaware of the goals, may be unaware of the strategies, and they may be unaware of the payoffs. We want to explicitly model the fact that they do not know the true game topology. And that's different than how game theory is often used, where we sort of assume perfect knowledge, or we assume that all players know the game structure. So these games are non-cooperative, they're very non-symmetric, the goals are not necessarily directly conflicting, they can be orthogonal. This makes things very complex to model. My goal is not to prevent an adversary into my network. That's not the reason I have a network. I have a network in order to do real work, so that's my real goal, and ancillary to that, I want to be able to prevent exfil and prevent misuse. The adversary has a very different goal in mind. So these games are also sort of simultaneous games. These are difficult to model because we don't control the pace of the decisions being made. We don't control whether an adversary indefinitely waits or whether an adversary repeats an action many times. So this makes, as Tiffany was alluding to, makes some of these games very difficult to model because they may be non-computable. So we tend to not look at formal analysis of some of these games, but more simulation. So we might try to simulate, over some period of time, what the outcome of the game would be, which makes things a little easier, but less rigorous. So I'll present what we're calling a hypergame scenario, where we're going to manipulate the game topology itself. And so we think this is important because it allows us to explicitly model the false information that an attacker has about the game structure. So we've added some notation to what you'd traditionally see in games. We've got a game, an attacker, defender, and we have moves that are annotated as being either a defender move or an attacker move. We have payoffs also annotated similarly. And then we're sort of inspired by conditional probability notation to say we have moves as perceived by the other player. And this is important. It means that I can have a perception of the attacker's move. The attacker can have a perception of my move. And those perceptions can be false. So they can be entirely false, meaning that move doesn't exist in the other game tree. So here's an example. In this case, the global game tree consists of two independent games. and these games are from the different players' perspectives. And the important aspects here are these dashed lines that show information sets between the two trees. So in this case, we have an omniscient defender. So we assume the defender knows everything about what the attacker can do and what their model is. That's going to be a bad assumption in the real world. But for simplicity, that's what we've done here. So the attacker does not know the difference between the real database server and the decoy database server. So when they log into this, if they're a naive attacker, they're going to think they're on a real database server. So in the attacker's context of this game, they are going to say, the defender, they might notice me connecting to this database server, and they can either do nothing, they can block me, or maybe they'll throttle me to see if I'm going to go away, because I don't want to degrade my normal users. So they don't see the defender take any action, so the blue box is the defender action, and they're going to attempt to log in. And so they might have some attack against the login method used by this database server, maybe just repeated attempts, maybe they've got a password file. So they're going to continue doing this because there is no penalty for failing. And this is a common method of attack. So they can continue doing this until they get blocked or denied or until they succeed. So they think they're going to get a high payoff down this leftmost path in this game tree. But fortunately, they're actually in the defender's context. And the defender has at their disposal other strategies that the attacker does not know about. So we can administratively disable that login. It's not a real database server. There's no real data. So there's nothing really at risk. What we've done is we've sort of swapped out, the attacker. We've presented the attacker at what we're calling a suboptimal play, a suboptimal strategy. We're poorly configured. This database server is vulnerable. And we're luring them into interacting with it over a long period of time. And so when they continue to attempt this login failure, they're incurring a delay, a cost. And that cost is imposed over some long period of time. So that could be short, that could be many days. It depends upon the sophistication of the attack, what kind of technique they're using. So in the end, they're going to pay a high negative penalty because they've interacted with this, we've kept them busy, while we've actually fixed the real database server that might have the same vulnerability. So this kind of model works just as it is. We can implement this. So this is an example. This is not a model that we created in the abstract. This is a model of what we've implemented, and a single game that we've implemented. And the idea here is that we can take and simulate this, and we can simulate it using the abstract model. We can also implement it and test it with real live red teamers. And if we get to it, we'll even put it on a real network and have real adversaries faced with something like this. It's much harder to get approval to do, but we'd like to sort of present real adversaries with real vulnerabilities and say, please attempt to attack the system. We'd like to see how successful you are at doing so. So we think that deception can be naturally modeled by allowing us to make strategy, structure, policy, game policy changes, structural changes. So basically looking at the game tree as something that's manipulated by either one or either player over time. And this means that we don't have just a game tree, we have a successive sort of set of game trees that as the game is played, we end up with a new game tree as new strategies are added, as parameters are changed, and then we have a history of game trees over time. And then we can continue down this path of, okay, we assumed an omniscient defender, what next? We need to assume the defender is no longer omniscient, and now we have an additional game tree. We have the true game tree that consists of all players' models of the world as well as the true state of the systems and network. And then we can do sort of the spy versus spy, like infinite regress, where the defender can have a model of the attacker's model of them. So each player can have a model of each other and that player's model of their own misconstrual of the game environment. So it gets very confusing very fast, which is why we need annotation and we need nomenclature to describe players' perception of the game environment and the parameters. So we talked about a game tree model, extensive form game that is a hypergame model where we are manipulating the game state over time. We can use this for simulation of adversary optimal strategies, and then we can undermine those optimal strategies by swapping out components, by showing that they're not interacting with a real system. If the adversary is aware of deception, this means they're going to react to deception itself. A valid strategy is telling the adversary, I'm using deception, and observing what their behaviors would be. Does that mean they stop interacting with your system? Does that mean that they change or are biased against interacting with certain hosts because they look more vulnerable than not? And then we can also look at multiple attackers. So we can actually extend this game environment very easily by adding additional game trees representing attackers and even corroboration between attackers. And lastly, I'd like to mention that we have a new cyber deception mini track in the government, digital government section of HICS. So this is in January of 2020. I welcome you all to submit papers. This will be a really nice sort of venue for us to attend, get back together again, and talk about deception for cyber defense. We also have a new technical group at Human Factors and Ergonomics Society. And this is new for the HFES community. So the human factors world has done cyber work, but it's just coming to a head where we think that if we bring more cyber folks into that environment and start educating them on computer security topics, especially since we're talking about deception now, and this has a lot to do with human psychology and usability and privacy. And so with that, I'll take questions. Thanks.